Mickelson, CEO of Virtuoso Software. I'll be presenting the effective development and test of embedded software using custom virtualized hardware at the Inventors Showcase. That's on Thursday, August 23rd from 7:30 to 9:30 p.m. in the Grand Sonoran E Ballroom. The video that follows is a fairly comprehensive overview of how the framework works, but I hope to see you at the showcase so you get the chance to play with it yourself. This is an introduction to the Virtuoso Embedded Virtual Device Framework. We'll start by creating a new C# host application. First, run Virtuoso. Now click the New Project tab. Click Visual Studio 2013 and create a new C# project. Create an example project folder on the desktop and name the project Example Host. Click Create Project. The host schematic opens with an empty schematic on the right and a component toolbox on the left. Drag and drop an LED from the component toolbox onto the schematic surface. Now right-click to the left of the LED to add a momentary push button. This is another way of adding a component and could also have been done by dragging and dropping from the toolbox. The push button has a Boolean output port named isClicked, which is true when the button is pressed and false otherwise. The LED has a Boolean input port, isOn, which sets whether or not the LED is on. Wire the isClicked output to the isOn input. Save the host, then update the host project by clicking the Update IDE button. Now open the host project in Visual Studio 2013 by clicking the Open in IDE button. Note that the host IDE is Visual Studio 2013 for this C# host plugin, but may be a different application for another host plugin. MainWindow.xaml is open by default. For C# hosts, MainWindow.xaml is the main window for the host application. You'll see the LED and push button components in the view, stacked on top of each other. Move them in the desired position, then build and run the host. That's it. You've now created your first C# host application. Click the push button and you see that the LED flashes when you click. You created a C# project using the Virtuoso core framework. Open the Virtuoso core folder and you will see a base host viewmodel.cs file. This C# file is emitted by the core framework for you as a reflection of the host schematic. The host viewmodel.cs file inherits from the base host viewmodel.cs file, and you can change this file however you like to extend the application functionality. You can also add components to the MainWindow.xaml view and add your own functionality. The Virtuoso framework will track its changes versus your changes and allow you to push new changes from the schematic without overriding your changes. Think of the schematic design as the first design stage, with the underlying host language design as an optional second stage. You can just use host components and the schematic editor to implement your design, or you can extend the design with complete flexibility to accomplish anything. The Virtuoso ecosystem is built entirely from Montage packages. The schematic editor, the C# host plugin, and all the targets in Virtuoso are all Montage packages. We can add packages as needed to meet our requirements. Virtuoso is entirely built using extensible Montage packages. The vault in Virtuoso's program data folder stores all the packages. Let's add the Touch LCD display package to the vault. First, we'll close Virtuoso and then add the Touch LCD component by dragging it into the vault. This is equivalent to shopping for a component on the Montage marketplace using the Montage launcher. Run Virtuoso again and open the example host. We can see the Touch LCD is now available in the toolbox. We could also easily write our own component in C# and add it to the vault. We can delete the LED and push button. drag and drop the touch LCD onto the schematic. In the property window for the LCD, you will see that the display is configured as a 400 by 240 pixel monochrome display with a green backlight. The pixels are a light gray when logically off and black when logically on. The backlight intensity is simulated by a floating point input value ranging from 0 to 1.0 on the LCD backlight intensity input port. We can see how our LCD will look using the intensity preview window. Let's hook up a knob control to control the backlight at runtime. Now in the property window, change the maximum value to 1.0 and connect the knob's knob value output to the LCD's LCD backlight intensity input. The color transition of the port connection from orange to green indicates that the port value type is being converted from a double precision value to a floating point value. Push the changes to the IDE. Let's get the components positioned properly, build, and run. We now have a WQVGA LCD display with a PWM backlight intensity we can control with a knob. Let's take a quick look at the host code to see what's going on. In the base host viewModel class, we see a touch LCD display viewModel property and a knob viewModel property. We also see the properties getting initialized in the base viewModel's constructor. This is all standard C# programming. In the connect method, we see the knob viewModel's knob value iDoubleProperty interface has a value changed event, which is getting registered with the Lambda expression event handler, which sets the LCD display viewModel's LCD backlight intensity value to the new knob value. In the main window view, we see the touch LCD display and knob XAML code with data context bindings to their respective component viewModels. In Virtuoso hosts, each component may or may not have a corresponding visual element on the view. If it does, it binds to its corresponding viewModel using the standard model view viewModel design pattern. If we want to add standard WPF controls to our host and add our own programming, we can do all of that without affecting the Virtuoso development workflow. The touch LCD has two analog output ports, touch X coordinate and touch Y coordinate, which indicate the position of the LCD being touched. Add two analog gauges to the schematic and wire them up to the X and Y coordinates. The X and Y coordinates are output as 32-bit integers, but the analog gauges accept a double precision number. However, there is port component metadata which provides the correct C# code snippet to convert from the 32-bit integer to a double precision value. Our touch LCD is a 400 by 240 pixel WQVGA resolution by default, so we need to update the range of our analog gauges to 400 and 240. Let's go ahead and give the analog gauges a name and also specify the unit of the gauge value in pixels. Push the changes to the host and position the new components. We can now build and run the project, and when we click and drag our mouse in the LCD, we see the X and Y positions displayed in the gauge. That was all core framework functionality using the framework to develop just a standard C# project. Now let's see how we can use Virtuoso to build virtual hardware for embedded software development. We will implement an embedded system that uses the touch LCD display and a Bluetooth module using FreeRTOS as our operating system. To use these packages, they just need to be in the vault. These packages include the FreeRTOS target template and the Bluetooth interface proxy component, which will allow our target to interface with a physical RN4020 Bluetooth module for real-world Bluetooth communications. Let's reopen our host application in Virtuoso. Now we see we have a QuickDeck component group with a Bluetooth module and 2 more FreeRTOS target templates. The Visual Studio 2015 target template is grayed out because this is a Visual Studio 2013 host. Let's add a target so we can get started with actual embedded software. Drag and drop a FreeRTOS target and name it FreeRTOS target. Click the Create Target button and Virtuoso will create a new C++ project to the Visual Studio solution and load in the FreeRTOS template code and sample task. This FreeRTOS target template also comes out of the box with a timer interrupt input and a Boolean output to flash an LED. Let's take a look at the Visual Studio host. We now have a C project named FreeRTOS target added to the solution. The project runs FreeRTOS and comes with 2 tasks set up by default in LED flasher task.c. The first task blinks the LED and the second task is available for development. The template includes a default hardware.h hardware driver interface with driver functions to control an LED. This LED driver is implemented in the sim hardware.c file for the virtual LED driver. This driver simply writes the value to a sim flasher LED state variable. Let's add a timer to the host and configure it to tick every millisecond. Hook it up to the target's Virtuoso timer tick 1 millisecond event, and let's also add an LED and hook it up to the sim flasher LED state output. Delete the analog gauges to make some room on the host. Push the changes to the IDE and let's run the project and see that LED flash. We are now running an embedded application with FreeRTOS, receiving a timer interrupt and using it to blink an LED. We can add other interrupts and variable binding ports ourselves. To see how the interrupt and digital output were configured for the target, let's add new variables for our application. We will want an analog input and a digital input to display input changes to the LCD, and we want to drive the LCD screen with a byte array that has encoded display data. Open hardware.h, our driver header file, and now let's add functions to read the analog and digital input and write to the display buffer. Open the sim hardware.c source file. This is the file that will implement the virtual driver abstraction layer for our virtual device. Our physical hardware build will use a different file, which implements the same exact driver API as defined in the header file, but will access hardware registers instead. You will see in this file that all the LED driver was doing was writing to a variable. Add the simulated analog to digital converter, push button, and LCD driver code as shown below. This simulated driver code simply reads from or writes to global variables. For the LCD display buffer, we are writing to a 400 by 240 by 2 byte display buffer, which will contain data encoded in RGB 565 format. For our virtual device, we simply need to write to the buffer. Now open the LED flasher task.c file so we can modify the application layer. Replace the application code in miscellaneous task 2 with the code below. This will read the analog input and push button and update the LCD display with a circle. The analog input will determine the radius of the circle displayed on the LCD, and the push button will determine whether the circle color is green or red, depending on whether the push button is pressed or unpressed. Build the project. The project would now run on the computer as a C program. However, the variables being accessed would not simulate real hardware. Now that we have compiled the project, we need to expose the variables on our target model in C#. Go back to the schematic and select the target component. Click on the Target Model Builder button to open the Target Model Builder. Here we will see the tabs for variable bindings, interrupts, upstreams, downstreams, and events, which we can expose on our target model. We can see the flasher LED variable binding and the timer interrupt have already been configured to be exposed on the target model. The LED is exposed on the target model as a Boolean property interface, and the timer interrupt is exposed as a simple method call. Add the analog input by going to the Variables tab and clicking New in the lower left-hand corner, then typing analog. We can see the list of all the global variables compiled in the target that match the entered string. Select the sim analog input variable. The default I/O direction and binding type of input and float are correct, so just hit OK to add the variable as a C# property on the target model. Right-click in the tab area and click New to add the digital input. Select the sim push button variable and change it to a Boolean input binding. Add the sim LCD display buffer byte array as an output. For this variable, change the change notification for the variable from auto to manual and specify the sim LCD display buffer changed flag as the change notification variable. Instead of the framework scanning the byte array for changes directly, it will just monitor the flag to see when the buffer has been changed to reduce overhead a little. There are other advanced variable binding operations which we won't get into for now. Close the Target Model Builder. Our target model now has the analog and push button input ports and the LCD display buffer output port in the schematic editor and on the target C# class. Delete the knob and its connection to the LCD backlight. Drag and drop a microchip curiosity board which has an analog input as well as buttons and LEDs. Wire the curiosity board's pot output to the target's analog input and wire the M-Touch output to the target's push button input. We also want to change the display format of the LCD to RGB 565 to make it a color display. Connect the target LCD display buffer to the LCD's input display buffer. Delete the LED and wire the target's sim flasher LED state to the curiosity board's LED1 input, and wire the LCD's LCD is touched output to the curiosity board's LED4 input. Save the schematic and push the changes to the host. Go back to the IDE and open the main window to position the new components. Save the C# project, build and run. When the curiosity board's potentiometer changes, the application draws a red circle with radius determined by the potentiometer analog value. When the M-Touch button is pressed, the application displays a green circle instead of red on the virtual WQVGA display. Touching the LCD display causes LED4 to light up. Set a breakpoint in the application task where the check for a change to the analog input occurs. Step through the changes to see how responsive the debugging is compared to in-circuit debugging. Now we want to add a Bluetooth RN4020 chip to our host so our virtual device can communicate to a mobile app using Bluetooth for system-level development. This way, the mobile app developer can simply pull the latest changes to the virtual device during development and doesn't have to hassle with programming or working with hardware. Drag and drop a QuickDAC RN4020 proxy component to the schematic. The QuickDAC RN4020 is connected to our host and enumerates on COM5, so select COM5 as the communication port. The QuickDAC RN4020 has a port to control power to the physical RN4020 chip, as well as ports to interface with all I/O associated with the physical RN4020, such as hardware and software wake digital inputs, event and device connection digital outputs, and UART communications. Connect the LCD's LCD is touched output to the RN4020's Bluetooth powered input. Update the host, position the RN4020 proxy's view component, and then run the host. By clicking the virtual LCD, we can see that the Boolean output is being routed to the QuickDAC RN4020 to turn the power on and off to the RN4020. Thus, the QuickDAC RN4020 is proxying the input on its Bluetooth powered port to control what's happening on the actual board. We will want to be able to send data to the mobile app using a virtual UART. Open the target model builder and add an upstream called RN4020 transmit stream. Note that the target now has an RN4020 transmit stream output port, and Virtuoso.h has been updated with the # symbol for RN4020 transmit stream. Add code to the driver header file to be able to transmit data to the UART. Now for the virtual driver, implement the driver as shown. This virtual driver passes the stream data to the framework and specifies the stream port using the RN4020 transmit stream handle emitted in the Virtuoso.h header file. Add code to the application task to transmit a test string when the M touch button is pressed. Now build the C project. In the schematic editor, add a console terminal control and wire the target's UART output to the console terminal's in-stream 1. Then wire the outstream 1 to the RN4020's transmit port. Configure the console terminal to forward the data received on in-stream 1 to outstream 1. The console is also configured to forward manually typed data to the RN4020. Push the changes to the host, rearrange the components, build and run the host.